Thank you, Sue. And there will be a special kindergarten exam at the end. I'd like to give credit to my collaborators and co-workers. As Sue mentioned very generously, Tamas and his group developed these tools. Well, Tamas didn't write a single line of code, so I cannot take credit for that. The people, there are lots of people listed here. The ones in yellow are students, some of them are still here. And I put the list in alphabetical order so that I don't offend anybody. I'd like to split this talk into three parts. One is just a general introduction to what space weather is. Even though Joyce claimed that she knows the word reconnection, yes, you do. We go a little bit beyond that. After that, I will give a little bit of obnoxious historical recollection of how science progresses. And at the end, I would like to show some of our own simulation results, which are mainly due to the people whom you saw on the previous view graph. So the general definition is that space weather is conditions on the sun and in the space environment that can influence negatively technological systems or can endanger human health or life. And as you can imagine, in our solar system, all space weather originates from the sun, and the main space weather initiators on the sun are solar flares that basically are localized, very short-lived brightenings of the sun. There are so-called coronal mass ejections, and the most dangerous coronal mass ejections, as the name shows, a mass ejection is when the sun basically burps and spits out a lot of material. And the most dangerous coronal mass ejections are the ones that are directly coming to us. So if you look at the sun, like in this picture, when there is a coronal mass ejection coming from the sun towards us, it appears as a halo all over the sun because it's from all sides is coming directly to us. So the most dangerous CMEs are the so-called halo CMEs. And eruptive prominences are also associated with space weather events and also with both flares and CMEs. I did a little bit of research for this talk. I wanted to know who was the first who actually used the word space weather. And it turns out that, just like for anything, scientists are sometimes they have high levels of vanity. And there was a symposium somewhere in Brazil about who was the first to use space weather. And at the end, you know, I don't want to name names. Andy was not there. But a number of very mature scientists competed. The winner was Tommy Gold, who actually is also credited with inventing the word magnetosphere. And in 1959, he basically was the first to compare space predictions or future space predictions to meteorology and weather predictions. So even though he did not use the word space weather, the general agreement at this symposium was that we should credit Tommy Gold. And 59 was just a few years after the launch of the space satellite. So this was the beginning of the space age. So how does space weather impact us? Space weather, as I mentioned, originates from the sun, and the coronal mass ejection emits or ejects a lot of material. This material propagates through the interplanetary space, and typically 1 to 2 days later it reaches the Earth, where it interacts with the magnetosphere. And the magnetosphere, of course, is the volume of space that is dominated by the presence of the intrinsic magnetic field of the Earth. And there are many space feather related phenomena. The most spectacular is the aurora. And when we see aurora in Michigan or even in Florida, we know that we are experiencing a large space weather event. The very first space weather event was observed in 1859 when a very wealthy amateur British astronomer, Richard Carrington, was observing the sun. And he was the first to detect the appearance of a solar flare, a local brightening on the sun. At this time, there were already magnetometers all over the world. Kew magnetometer. Kew is a suburb of London, so it's basically near London. There is Bombay, and you can see the magnetometer deviation in Bombay was extraordinary. This is 500 nanoteslas. The terrestrial magnetic field is something like 40,000 nanoteslas. So 1,000 nanotesla disturbance is huge. And even in Bombay, India, which is at pretty low latitude, there was a huge disturbance. A few days later, September 2, was when Carrington observed the solar brightening at the very end of August, August 31st. September 2nd, there was a huge magnetic storm. This is when this happened. And the telegraph, at that time, there was no other technological system that was sensitive to space weather. But the telegraph between Boston and Portland, Maine, worked for hours without power. It worked on celestial power, as they called it, which was pretty amazing. So why do we care about space weather? We care about space weather for many reasons. Astronauts, of course, get a lot of radiation, and during space weather events, the radiation increases. Spacecraft can be lost due to space weather events, and I will talk about it a little bit more, because radiation can either penetrate into the spacecraft or destroy some of the microelectronic elements. Navigation errors are very important, and they are increasingly more important since our dependence on GPS is increasing. And especially the military, for instance, doesn't want to try to send down a cruise missile on a chimney, and then they miss it and hit a hospital. And the most important space weather effect is the so-called geomagnetically induced currents, which can impact power systems, and in the worst-case scenario, they can create blackouts for a long period of time. Some of the space weather hazards that are related to spacecraft, you can degrade the solar panels and shorten the lifetime of a spacecraft. You can degrade the electronics and create either single event upsets when a bit is reversed, or completely destroy microelectronics. This is a very revealing image. This image is taken by the SOHO spacecraft, and it is a coronagraph image, which means that there is a disk that blocks out the sun so that we can see the corona, the solar corona. And under normal circumstances, this is how a solar image looks on the SOHO spacecraft. During the main phase, or the most important initial phase of a space weather event, a solar storm, a lot of solar particles are ejected from the sun, and they propagate along magnetic field lines towards the Earth. And when they hit the SOHO spacecraft, the hits basically look like snowing on the image. These are all particle hits on the detector. And in some cases, some extreme cases, it can blind detectors completely for minutes or even for longer periods of time. October 2003, there were the so-called very famous Halloween events. And it's called Halloween events because there was a series of solar storms from early October to early November, and one of the biggest storms occurred on October 29, and that reached Earth on October 31st, which happens to be Halloween. So during the Halloween event, there were power outages in Sweden, for instance, and these are just two images of burned down power stations and transformer systems. The problem with these transformers is that they are individually built. So if the construction cost is not that much, it's a few tens of millions of dollars, but to replace one takes about 6 months. So if a space weather event knocks out the North American power system, the big damage is not the replacement cost. The big damage is the economic impact, that basically you lose production in large areas for weeks or months. In the United States, power was reduced in nuclear facilities. In South Africa, 14 transformers were damaged, and the basic commerce and security got impaired. Another issue is the astronaut safety. Here I'd like to talk a little bit about doses, since we all get radiation all the time. There is a difference between the absorbed dose and absorbed dose equivalent. The absorbed dose equivalent basically measures the radiation energy that is corrected for the absorption by a certain type of biological tissue. Certain tissues are more sensitive than others. For instance, an eye is much more sensitive than the skin to radiation. And the units what people use is 1 sievert, and 1 sievert is 100 rem, which this unit, the rem, was invented before feminism, because the name stands for Röntgen equivalent man, which is not Röntgen equivalent woman, right, as it should be. And there are various shieldings available on spacecraft. There is a spacesuit, which is very thin. It corresponds to about 0.3 gram per square centimeter of aluminum. And it goes up to the shelter, which is about 10 gram per square centimeter. So these are the astronaut radiation limits. For the BFO, it stands for blood-forming organs, like the bone marrow, the skin, eye, and testis. And these are the doses what you can get, you are allowed to get. And the carrier max is about 400 rems for the blood-forming organs. These are astronaut lifetime limits set by OSHA, and OSHA is very cautious. It increases with age, and it's different for men and women. But for an older man, the lifetime limit is 400 rems. So how does this compare to some events? The Apollo 16 mission astronauts walked on the moon in April of '72. There was Apollo 17, December '72. And in August 1972, just between the two, there was a huge event. And these are the calculated doses what an astronaut would have received. Inside a spacesuit, about 400. And there was no space station at that time, but inside the Apollo, about 100 rems. Now, this compares to these limits. Worldwide average is about 1/4 rem per year. The jet plane crew gets about twice as much. 1 CAT scan is 1 rem, And the deadly dose is about 300 rems in a short time, because the human body is capable for regenerating. So if you get the 300 over a long period of time, it's not deadly. But if you get it within 1 day, it is. So just imagine that this August event would have given 400 rems inside the spacesuit. The last thing NASA wants for publicity is to bring back a dead astronaut. GPS. We depend more and more on GPS, and GPS accuracy can be greatly degraded by space weather events. This is when the accuracy goes down from centimeters to tenths or even hundreds of meters sometimes. And the impacts range from recreation. One of the two emergency services, one of the newest thing is precision agriculture, when, for instance, the heavy equipment on the field is completely controlled by GPS. You pre-program the route, and the equipment follows it with centimeter accuracy. You don't need people anymore to do this work. And of course, when there are space weather events and the accuracy goes down to tens of meters, you might enter into someone else's field. Scales in space weather research range from the sub-second, a fraction of a second, and a few centimeters to the size of the solar system. I used a binary system here, both for spatial and temporal scales. And you can see that there is about 28 orders of binary magnitude difference between in spatial scale and temporal scale. And this means that with a three-dimensional time-dependent simulation, you need to you need to span 28 binary orders of magnitude in all 4 dimensions. It's just not doable. So the answer is that you need to, if you want to model and understand the space weather and its impacts, you really need a system that couples together a number of models so that you can basically describe all the important physics. And we will get back to this when I will talk about what we did in Michigan. The good news is that presently there is a large heliophysics observatory system that is available to study and measure space weather, and these are only the civilian satellites. In addition, these are only the NASA satellites, actually. In addition, there are NOAA satellites orbiting the Earth and a very large number of military satellites that also observe space weather. So after introducing the concept of space weather, let me get to the second part and talk a little bit about the evolution of ideas. I need to remind you that old ideas never die, but scientists do. Or if you paraphrase it, science progresses one funeral at a time. We invest so much time and energy into our ideas that we never like to give it up. And let me just give a few examples. In 1889, the president of the American Association for the Advancement of Science, AAAS, who was Samuel Langley. By the way, the Langley Research Center, the NASA Center, is named after him, observed that the scientific community behaves as a pack of hounds, where the louder voice bring many to follow them. In other words, if we do science, there are always the quote-unquote leaders who set the tone, and most of us just follow them. Here are some examples. In 1892, Lord Kelvin, who was the president of the British Royal Society at that time, gave his presidential address. And he said that we may also be forced to conclude that the supposed connection between magnetic storms and sunspots is unreal. And the reason why he said that, because at this time, the most efficient energy production known to humans was burning coal. So he took 100% efficient coal burning, extrapolated it to the sun, and decided that the sun cannot have enough energy. In Sidney Chapman, who was one of the great individuals in space physics, and a lot of good things came from him, but also a lot of bad things, was working on the problem of the solar wind. This is the plasma that is coming from the sun. And he wrote in one of his review papers that around 1920, when he was a professor at Manchester, he tried to solve the problem of a continuous magnetized plasma flow interacting with a dipole, magnetic dipole, which is exactly how the solar wind interacts with the Earth. But being a mathematician before being a physicist, he basically concluded that he couldn't solve this problem. Therefore, if I can't solve it, nature certainly will not do it. So instead, he took on a PhD student. His name was Ferraro. And Ferraro's thesis was to solve a problem what Chapman knew is solvable, which is you take a blob of plasma instead of a continuous plasma and calculate the interaction of a blob of plasma with a dipole. They could solve it, published it, so Chapman got convinced that this is the situation in interplanetary space, which must be empty because there can be no permanent radiation coming from the sun, because I cannot solve it. 1957, by 57 there was quite a bit of evidence that there must be some corpuscular radiation coming from the sun. And a young postdoc with a very bad scientific pedigree was working at the University of Chicago, working for John Simpson, who was one of the most famous space scientists at that time. And he basically came to the conclusion that there can be no steady solar corona, only a continuously expanding corona, the solar wind. Chamberlain, who was a more senior scientist and professor at the University of Chicago, basically said that Parker's large expansion velocities result from an invalid assignment of an integration constant. And Chamberlain basically said that there can be no solar wind. This was 1961 actually. 1962, the Mariner 2 spacecraft observed the solar wind, continuous solar wind, for 3 months. Chamberlain, however, never gave up. Even in 1990s, he explained that Parker's primitive idea was wrong, was right for the wrong reasons. Again, scientists never change their mind. Old ideas never die. Field-aligned currents. Birkeland in the early 20th century basically concluded, Birkeland was a Norwegian physicist who spent his life in a country where aurora is prevalent. And he came to the conclusion after his observations that aurora must be related to intense electron beams coming along magnetic field lines. And Chapman, who was basically ruling the field, he was the unquestioned dictator of space science until the late 1950s, basically said that Birkeland had the invalid conception of intense electron beams mingled error inextricably with truth. And Chapman, this was in 1968, Chapman declared that there cannot be field-aligned currents, period. And it was after Chapman's death in the 1970s when finally, experimentally, it was established that in spite of Chapman's insistence, there are field-line currents. And they represent the major interaction between the ionosphere and magnetosphere. So these were the biggest fights and important sub-fights in science, space science. We participated in a fight which is much, much smaller scale and less important, what I call the Code Wars. In the early 1990s, there were two global magnetohydrodynamic codes in the United States. One came out of the Naval Research Lab, NRL, and that is called the Lyon-Feder-Moberi code. And the second one came out of UCLA, and it is called the Open GGCM code, at least today. They both use some pretty advanced technology. But in the early 1990s, something unacceptable happened. This was shortly after Phil Rowe joined the Aerospace Department in Michigan. Phil Rowe is well known in computational fluid dynamics. He is a brilliant applied mathematician who, together with Bram van Leer, who was also in the Aerospace Department, really revolutionized computational fluid dynamics and made fundamental contributions. So Ken Powell was a young assistant professor in the early 1990s. And Phil Rowe had this idea that the MHD equations look incomplete. And if we could basically extend the equations to make them less degenerate, and I don't want to go into the mathematical degeneracy, then all the toolbox of modern computational fluid dynamics could be used for magnetized plasmas. And Phil had an idea how to do that. Ken Powell worked it out. And the main idea was to leave the divergence B in the equations and not drop it, as most people do. Now, we all know that in our universe, divergence B is 0 because nobody ever observed magnetic monopoles. But those of us who are old enough to remember know that in the 1970s, there was a very expensive major hunt for magnetic monopoles. This means that the absence of magnetic monopoles is not a fundamental law of nature. It is an observation in our universe. So Ken Powell's and Phil Rowe's idea was that let's keep the divergence B term, the magnetic monopole term, in the equations, knowing that it is 0. But if we just keep it, it will change the mathematical structure of the equations. And what happens is that if you calculate the normal, the eigenmodes, the eigenvectors, the characteristic vectors of this equation system, you get one new wave, which is the divergence B wave. And if you include this wave, suddenly everything falls in place, and everything, all tools developed for CFD, computational fluid dynamics, can suddenly be used. So this, of course, created the code war because we were the newcomers, the new kids on the block, and the established groups tried to basically kill us before we grow up. They basically made a lot of claims that all turned out to be wrong. They complained that div B is 0 to truncation level and not to round-off error, questioned correctness of the magnetic topologies. They questioned whether there are spurious currents. They basically claimed that our code is highly diffusive, and the main code, the main line was that diffusion hides all weaknesses. So these became urban myths, and even today there are people who parrot them. But this was in the early 1990s. We all get older, we get old, a little bit less aggressive. So the code wars basically subsided into a war of attrition. So what did we do here in Michigan? I'd like to give credit where credit is due. In the present code, what we use today, the main code developers are Gabor, Igor, and Bart. Darin made a lot of contributions, especially at earlier days. Aaron also contributed quite a bit. I will talk about various coupling things, but if you just look at the names, there is a group that, including Valerie, who is doing the kinetic codes, there is a small group of code developers, 4 or 5 people, who really are behind everything what we do. And then there is a group of leeches who use it. And of course, quoting the tension between the code developers and the prime users is the tension that really leads to the improvement and further development of the code. There is nothing more inspiring than when Aaron comes in and says that this code sucks. So this is the basic architecture of the space weather modeling framework. Frameworks are reusable. This is the definition of frameworks. It's basically a software architecture that can incorporate a lot of flexible and interchangeable modules. The source code is presently about a few 250,000 lines of Fortran plus a bunch of wrappers and couplers, mainly written in MPI and Perl. And I don't think we have Python yet, even though we sooner or later need to move there. There is an infrastructure layer, a physics module layer, superstructure, and user interface. And if you have a physics model, it can be incorporated into the framework with relatively modest investment. The main idea is that because this couples together many independent models that describe different physics, therefore, if you couple a model to the framework, it is automatically coupled to all of its existing components. So you can do extended physics relatively easily. Presently, this is the block diagram of the present components of the framework. We basically go from the sun through the interplanetary space to the inner heliosphere. We do simulate the outer heliosphere, the magnetosphere, and these are many components of the magnetosphere. And the framework is capable to incorporate observations from solar magnetograms to flare observations to upstream monitors and ionospheric observations. And basically, you can run either the whole or any subset, any meaningful subset of this framework. The physics is quite sophisticated. It's again a block or highly modular infrastructure. You can choose your time stepping, you can choose your conservation loss, you can choose your numerics, you can choose your adaptive mesh refinement library, you can choose the source terms which basically describe the extra physics what you want, and these basically enable us to simulate everything from the sun to planets to the whole solar system. And then there are auxiliary equations. The Betsaras, which is the essence, the main, the magnetohydrodynamic code at the heart of the framework, of the space weather modeling framework, is a very efficient high-performance code. And this shows the so-called weak scaling on a very big supercomputer. And it has a very, very almost linear scaling to about 100,000 processors, and still 60% scaling. I think it's at 260,000 processors. There are two main applications what we use the framework for. One is related to the sun and solar wind and solar transients like coronal mass ejections. And Bart very modestly named this the awesome model, very appropriate. And we also do magnetosphere simulations where we don't simulate the entire solar system. And I call this MARCI, magnetosphere with ring current and ionospheric electrodynamics. And MARCI basically includes the magnetosphere, the ring current, and the radiation belt models. This is the physics in the awesome model. The main idea is that in order to heat the solar wind, we release wave energy from the sun along magnetic field lines, and we take into account, calculate all dissipation, or most important dissipation mechanisms, and self-consistently solve the wave energy equations with the general plasma equations for the plasma. And here are some results. This is I think this is 100 million, no, this is 12 million cell simulation, which shows the near solar region. The units are in solar radii, and you can see the velocity and the plasma beta, which is the ratio of the plasma pressure to the magnetic pressure. And for non-experts, one of the most impressive things is this is the adaptive grid. And you can see that near the sun we have tremendous resolutions. And there is very high resolution near the equator where large currents flow. And the resolution follows the shape of the magnetic inversion line. These are the latest. Using this model, we created synthetic images that mimic the images observed by the Solar Dynamics Observatory and the Stereo A and Stereo B spacecraft. This is for March 7th, 2011. And the different panels show different instrument wavelengths. You probably cannot read it. It's 94 nanometer, 175 nanometer, and each wavelength is basically sensitive to various regions and various temperatures on the sun. And the top line is the model simulation. The second is the observation. Again, simulation and observation. So for the SDO, we have 6 wavelength bands and simulated those. And for stereo A and B, we have 3 wavelength bands what we simulated. And you can see that these simulations really capture the observations very well. It's not perfect, but we get the active regions, the bright spots right. We have the overall intensities quite well. So the awesome model is probably the first global model that is capable to really simulate what we observe with these telescopes without massaging or introducing some very arbitrary parameters. This is, in this model, we can simulate from the sun to Earth and beyond. So this is the comparison between the in situ observations at Earth's orbit with the simulations. The greenish line is the observation, the whitish line is the model, and you can see that the velocity, the density, the temperature, and the magnitude of the magnetic field, we get very, very good agreement. In the magnetosphere, our standard model is which uses three components, as are mentioned: the global magnetosphere, the inner magnetosphere or the ring current, and ionospheric electrodynamics. This slide just shows the way we coupled the ring current model to the anisotropic Betsaras, and the anisotropic Betsaras means that we use anisotropic temperatures, different temperatures along magnetic field lines and perpendicular to the magnetic field lines. Without going into details, this is a pretty sophisticated advanced coupling between these two, and here are some results. The black line shows observations. This is the so-called, it's practically the DST index, which characterizes magnetospheric storms during a space weather event. And this characterization, the observation show is the black line. The dotted brown line is the simulation without assuming anisotropic temperatures. And the solid brown line is the simulation with anisotropic temperatures. And you can see the dramatic improvement. It's not a perfect agreement, but it is a very good agreement. And for the first time, I think we are pretty close to being able to predict space weather effects with these simulations. Here is a simulation for the Geotail spacecraft, again with and without the anisotropic temperatures. And you can see, for instance, in the X component of the magnetic field, the improvement is tremendous. In other components, the improvement is much smaller. The Community Coordinated Modeling Center at Goddard independently evaluated the presently available 3 global magnetosphere models, SWMF, OpenGGCM, and LFM, and also evaluated 2 empirical models, the VEGA and Weimer models. And the results of the evaluations for various levels of magnetic activity is shown here. The higher the magnetic activity, the more disturbed the magnetosphere is, the bigger space weather event. So it turns out that in all of these cases, except one, the space weather modeling framework came out first, and even when we came out second, it's a very close comparison. This is another validation study by CCMC, the Community Coordinated Modeling Center, where they separately evaluated another index for high latitude and mid latitude stations. And without going into the specific details, again, the space weather modeling framework beat all others by a significant factor. The point I'd like to make is that if you have a skill score which is about 0.5, that's when a model starts to be useful for actual prediction. And you can see that at high latitudes, we are just a little bit below being useful. But at mid-latitudes, we definitely are in the regime where the predictions are already useful and can be used for predicting. What is the future? We are working on new adventures and new developments. And this one is that reconnection, Joyce's favorite word, is very important in space weather simulations and understanding space weather. But reconnection is a very, very small scale phenomenon. So what we did, we our work, or what we are doing, mainly Gabor and Lars at this point, they are embedding a simulation box for kinetic simulations into a larger box of magnetohydrodynamic simulations, if this would ever work. No. Let me try again. Is it working?
Move the mouse into the movie.
It's not working. Well, anyway, it worked. This is the demonstration effect because it worked before. Anyway, so this shows that we can get a very smooth solution as you embed a kinetic simulation inside a global MHD simulation. And this is clearly a very important future way of simulating magnetic reconnection and magnetospheric dynamics. The other effort that we are working on, it's mainly Gabor and Valery, where we are coupling fully coupling, two-way coupling the Betsaras fluid code, MHD code, to a DSMC, a direct simulation Monte Carlo code, which will enable us to do things like particle acceleration and particle tracing in the magnetosphere. So these are the two big new efforts we are working on. And I'd like to conclude with just summarizing that we have a relatively large group in the Center for Space Environment Modeling. This is a long-term effort. We are doing this for over 20 years now. And the major application areas are the solar, heliosphere, and magnetosphere. And the next challenge is the PIC and DSMC particle in cell and direct simulation Monte Carlo. But the solar, wind, and the magnetosphere simulations are already gathered at the CCMC, the Community Coordinated Modeling Center. And the community is using them. And I think especially the magnetosphere is pretty much available and ready for predictions. And SWMF and its components are available for download after registration from our website. And just one very last comment, because it's about 20 people and over 20 years, it takes a long and sustained support to do this. You cannot just do it with a single grant over a short period of time. So coming back, are we having fun yet? You bet. Thank you.